So there's all the dipole moments cancelling out. Now, you might want to say, okay, I should have showed you this. How do you know they cancel out? If you can take them and draw a closed triangle. So watch this. If I take this one, I put it there. No, not that. No, that's supposed to be the middle. If I take this arrow and I put it there, and I take this arrow and put it here, you know, tail to head. And I'll take this one and put it here, tail to head. They make three sides of a closed triangle, which means, you know, being pulled this way, that way, and this way. So overall, you're not being pulled at all. Right. So if you can draw a closed figure with those dipoles as vectors, with the right kind of directions and the right kind of sizes, then there's no overall dipole moment. Now, if there's no overall dipole moment, that means that the molecule overall, now listen, this is quite important. If the molecule overall has no dipole moment, that means you've got an interesting situation. You've got polar bonds in the molecule, but the molecule as a whole is not polar. So the bonding is polar, but the molecule isn't. And that's important to note, because you'll see in that worksheet you're doing for homework, it's got the place to put the polarities, to put the shape and all that. And then it says, is the molecule polar? Is this a polar substance? Now, I've already shown you that polar substances like water have got particular properties. If it's not polar, then it's got certain properties that it hasn't got. So, for example, it can't dissolve polar substances. They won't dissolve in a substance that's non-polar. And you need to be able to decide, we're going to ask you, you know, which of these substances are polar, which aren't polar, and that kind of stuff. And you must be able to work it out based on the bonding and the shape, because it depends on more than just the bonding. All right. Okay. So there we go. We will still come back to this. This is quite an important topic. All right. So somebody said to me yesterday, what happens if, you know, there's that boundary of 2, if the difference in electronegativity is smaller than 2 but bigger than 0, it's polar. What happens if it's bigger than 2? If it's bigger than 2, it's ionic. So then the electron actually gets completely taken away. So that's what I'm showing here. You've got a sodium ion, chloride, sorry, sodium atom and a chlorine atom. If they come close together, the difference in electronegativity is so big that the sodium will lose its electron to the chlorine. Now, some people will talk in the terms of it'll donate the electron to the chlorine. It doesn't donate it, it gets taken. It's mugged. Okay? And the sodium becomes an ion. So now it's lost its outer electron and its charges are no longer balanced. It's now got an overall positive charge. Okay. The chlorine, and in terms of what happens to its properties, it's interesting. It now becomes less dangerous. Because sodium itself, sodium metal, is very dangerous. If you put it in water, it goes berserk. If you were to eat it, it would react in your mouth, produce hydrogen, it burn you really badly. It's dangerous stuff. Once it's lost its electron, it becomes a sodium ion, which makes up half of table salt, and you can eat it quite happily. Your body can still use it for all sorts of stuff, but it's not dangerous anymore. Right.
So is the sodium and the chlorine still together?
So what happens is this. Remember I said to him when I steal his iPhone, wherever I go, he's going to chase me. So now what happens is you can see the sodium atom has got a bit smaller. I know I didn't make it very clear, but can you see this thing here, the sodium ion? I've drawn it a bit smaller than the sodium atom because he's lost his electron. The chloride ion, this thing here, is a bit bigger than the chlorine atom. Why? It's gained another electron. The electrons all repel each other, so now they kind of swells them. And that actually happens in real life. So the sodium ion is smaller and it's positive. The chloride ion is negative and it's bigger. Don't miss this thing here. Chloride. How come chlorine became chloride? Any negative ion gets IDE on it. Okay. Cool. So there I've explained it in pictures. This is the electrostatic attraction from the positive to the negative, which makes the two of them stick together. And it's a strong bond. That's what keeps things together in an ionic substance. And that is basically an ionic bond. So there's it. That's it in pictures. That's it as a Lewis diagram. Now, for a Lewis diagram, you've got to show the whole thing. You've got to show the sodium and its electron, you've got to show that it gives its electron with an arrow to the chloride, not willingly. You must just know that. And then you must show that now the sodium is positive. So, Luke, that's obviously far more important than this is. Well, you will be sorry when I ask you this in your exam and you can't answer it. And the chloride has now become negative, and you need to show that all of that. So a Lewis diagram for an ionic bond could be worth 4 marks, usually 3. Okay, so that's it in pictures, that's the Lewis diagram, and that's it in words. We can ask you, we don't normally ask you the pictures, we'll normally ask you either the Lewis diagram or the words. Happy? Can I move? Good. Here's a couple of examples showing the formation of ions through reactions. So here's the formation of a positive ion. Potassium atom becomes a potassium ion when it loses an electron. Why do I put a plus there if it loses the electron? No, that plus there doesn't mean it's become positive. This plus here means it's become positive. So it's this building. Because sometimes guys want to put a minus there because it's lost the electron. Let's say this is the atom and this is its electron. Right? It's one little outer electron. Now, if it loses its electron, it becomes an ion, but its electron still exists. You have to still show it. If I put this back on there, then I get back to the atom. So here's the atom with its electron. Now it's lost the electron. There's its electron. If I put it back, then it becomes whole thing there. And then if you become a negative ion, obviously the atom gains electrons and becomes an ion. All right. So you must be able to show those. Do these quickly. I've done the first one for you. You're going to need 2 chlorines. The next one, I would do like that. 2 sodiums, each giving 1 electron to the sulfur. So you get sulfur 2 minus with 2 sodium. Now, this is I've got a bad habit. I'll keep the pluses inside the bag. They're supposed to be outside the bag. 2 aluminiums giving electrons to 3 sulfurs. Now here I broke all my conventions and I said 2 and 3.
Oh, so you could have told me that.
Yeah, please go shopping my pencils.
Yeah, but we're not going to wait for you. Right, can I carry on, Jim? Okay, so what we've got here, just showing you the formation of something that you've known about since grade 9. In grade 9, when you learned your valency table, when you learned your valency table in grade 9, you would have learned about the hydroxide ion, the OH minus ion. So what's an OH minus ion? Well, it's an oxygen, 1 covalent bond to a hydrogen, then it's got an extra electron from somewhere, and that gives you OH or HO minus. Right. Then you can also get these other species formed. We've discussed already the H3O plus. I'm not going to go there for now. They can just, we might come back to it later on. But for now, that's good enough. The hydroxide ion, right? You must be able to draw its Lewis diagram. Now let me talk a little bit about a concept called ionization energy, because this is what happens when you form an ionic bond. Remember I said to you, ionic bond, you get 2 ions formed. Ions are formed when the one atom takes the electron away from the other. When you take the electron away from it, you're making it into a positive ion. So we say it's ionization. You're creating an ion. Now the energy required to do that is called ionization energy. And that's a definition you must know. This definition up here, if I was you, I would highlight it, whatever, because we can ask it from you for 2 more. You have to get it word perfect. you can't leave out the gas phase bit of it. You can't leave out the word completely. Okay? Ionization energy required to remove an electron completely from an atom is a gas phase. So you must learn your definitions properly. So that's it in words. Here I'm showing it to you in pictures. Sodium atom, sodium ion, what's happened? It's lost an electron. The amount of energy required to do that is this, 494 kilojoules per mole. We don't expect you to know that number.
Is that universal?
What do you mean universal?
Every other-
No. So only every atom's got its own ionization energy.
It's a bit off topic because I'm like chemistry.
Yeah.
The atoms like never touch, right? They don't touch.
Theoretically, they don't. Yeah. So that is the theory, and it's supposed to be true because the reasoning behind it is this: as you reduce the distance between them, the force increases exponentially. So to make them touch, the force has to be infinite, and you can't use infinite force. Right. This is another bit of energy that you need to know about. This is the energy given off when an atom gains an electron affinity. Now, that's a bit of a strange definition, a strange name. You need to learn. You can ask you any of those. Yeah, it's just the opposite. It's the amount of energy released when an electron is added to a gaseous atom. Both of these take place during ionic bonding. Right.
They ask you for the definition. Do you have to put just always?
Yes.
accompany?
No. The definition is just up to you. Just that first sentence. Right. So those are two definitions. Emma, are you struggling to stay focused? But just vibing. No. Just the first sentence. All right, now. So I've told you about covalent bonding. What type of substances bond covalently?
Non-metal.
Non-metal. Why? If they pull on the electron strongly, they won't let go. What kind of compounds undergo ionic bonding?
Non-metals.
Metals and non-metals, because the metals don't hold on to electrons and the non-metals do. So what happens with metal? Metallic bonding. Okay. So how does metallic bonding work? This explains it. So because the metals don't hold on to the electrons well, the electrons can go walkabout. So this is supposed to be a microscope picture of a metal. You've got the atoms of the metal here. Why are they positive? Because all of them have lost at least one electron. Where's the electron gone? It's just gone walkabout. Okay? Because the metal doesn't hold on to it properly, it thinks, okay, so you start to bug me now. Okay. So it doesn't hold on to the electron strongly, so the electron can be attracted by the other atoms and the electrons can move across onto the other atoms. So what? Well, that means a number of things. Firstly, because the electrons can move, this thing can now conduct electricity, which is massively useful. If metals didn't have that property, we would have no electrical component. You know what life is like when S shuts down? What happens if electricity wasn't possible? Really didn't see the burn. Okay, and that would be the case if metals didn't exist. And metals are only metals because they don't hold on to the electrons very well. So it's brilliant design. Okay, we get all the metallic properties. The fact that these electrons can move around also means that if you smack a metal hard, the atoms can shift positions. The metals are malleable. So you can bash a metal into shape. So I mean, like you're playing with a piece of putty here. Putty is even more malleable, but metals are malleable. You know, are metals hard or soft? Now, most of us would say, no, geez, metals are really hard. Are they harder than non-metals? Actually, no, they're not. Give me an example of a non-metal. Well, like, how about rock? Stones. Now, that's not strictly true because stones aren't actually non-metals. Stones are mostly ionic. Stones are minerals. They're ionic compounds, right? But take a non-metal. What's a good non-metal? Diamond. Which is harder, iron or diamond? Diamond, much harder. So, okay, most non-metals are actually gases. There's very few non-metal solids. There are some of them, and if you look here, sulfur, phosphorus, those are both solids. So are arsenic and antimony, bismuth, but these ones are getting bigger. As they get bigger, the atoms get a little bit more wieldy. So these are non-metals, and they're quite big, but they're not that hard. But if you look at some of the small ones, carbon's hard. Okay? They make bicycles out of graphite for no reason. Hard. Now, metals are actually relatively soft. Metals, they're malleable. You can bash them into shape. You can make a nice looking hammer, or you can make whatever. You can bash them into shape. It makes them useful. All of those properties are because these electrons in the metals are not strongly held. So when you bash this metal on the side, the electrons can move out the way, atoms can change position. So if they're not strongly held, why don't they just fall apart? Well, when we say they're not strongly held, we mean they're relatively not strongly held. So these electrons, although they can go walkabout, now the electrons are negative. They form like a negative sea of negativeness around the positive atoms. And the positive atoms are strongly attracted to that negative sea of electrons. And that's what holds the whole thing together.
You bend the nets with a positive ion staying place.
Yes. Yeah, they do. So that's metallic bonding. And if you understand metallic bonding, all the metallic properties make sense. The conductivity of both electricity and heat, the fact that they are malleable, the fact that they're shiny, all of those can be explained from the metallic bonding. All right.
So what's shiny?
So why is it shiny? So shiny is quite a complex one. Shiny's got two things. So you can polish metals nicely. Why can you polish them? Because they're malleable. You can polish out the bumps and get them nice and flat. But then also because the electrons can move, if light hits the thing, the electrons can jump up to a higher level, absorb that light, drop back down, and reflect that light everywhere. That makes them shiny. All right. So, and this word here, sea of delocalized electrons. What does delocalized mean? They're not here local anymore. They're all over the place. You don't want your money to become delocalized. You want your money to stay in your wallet. Okay? Yeah, I won't go there. I won't say the other one. Right. I know this is jumping around a little bit. I'm sorry. This cycle, to be honest, isn't necessary. So I'm going to skip it. The Bourne Harbor cycle. Sorry? You can cross it out. I'm going to skip the Bourne Harbor cycle. We don't actually need it. I know this is not a great slide. If I get bored, I'll make it again. What that slide is showing you is the difference in conductivity between ionic substances and metals. Now, you guys all know metals conduct electricity under any conditions, yeah? What about ionic substances? When they're dissolved in water, or when else? Who's this? This is Emmanuel.
When they are not in the solid state.
But they're liquid. But when are ionic things liquid? When they're melted. Can you melt salt? Yeah. Yeah. So, I mean, look at lava. Lava is melted rock. Rock is minerals. Rock is ionic substances. You can melt ionic substances. As long as you do it in the absence of oxygen, then it won't burn. And when they're molten or when they are liquid, dissolved in water. So here, this is the ionic liquid or ionic solution. The ions are free to move. If you put a big positive charge and a big negative charge, the positive ones will go to the negative, and the negative ones will go to the positive. It'll conduct electricity. How does a metal conduct electricity? Do the positives move? No. But the electrons can move. So if you put a metal in a potential difference, the negatives will go to the positive side. And that's how they conduct electricity. But the positives will not move.
So for the ionic liquid, you will be able to see the shift.
No, we can't actually see the ions. And the ions are normally not colored. And if they have got a color, the color will be everywhere. So you actually can't see it. You can see it if you put an ammeter there or something, it'll show you that it's colored. Now, obviously, in an ionic solid, all the ions are held strongly in their positions. They can't move, so it can't go back. Happy? That's a little bonding summary. Shows you the 3 different types we talked about. Little explanation of them and a little thing about their properties. Just read through it to make sure that it all makes sense. If anything to ask me there, you've got 2 minutes. Just look at it.
What is it? D.
Don't draw this shit. You don't like it, I don't like it. I don't care.
What is it? You know.
What's the purpose of it? Say that again. What's the purpose of the man-made? So look, every element's got different properties. So now, if we can make another one, make some new interesting properties. They turn out to be not as useful because the bigger they get, the more unstable they are. So there's not a lot of uses for these. We're always very reactive, so we can't go close to them. And we can find uses, but they're going to be quite exotic uses.
What is the V? V low? Is it V and I? What's
Very low or very high. That's dissolving, that's bonding summary. But 1 minute, let me just explain this slide, because then we're done with the initial bit of bonding. Come, your parents have paid for this minute, we might as well use it. What's this slide? This slide is showing you how solids dissolve, or ionic solids dissolve. This here is supposed to be ionic solid, negative ions, positive ions. Don't pack up while I'm talking, it's rude. You've packed up already. I'll wait while you get your stuff out. So, you got positive ions and negative ions. Okay. What happens is if you put them in water, I've already showed you that water is polar. So the negative side of the water molecule will go to the positive ions, and the positive side of the water molecule will go to the negative ions. Lots of water molecules gather around these ions and they just pull them apart. Like piranhas attacking one of those little birds or something that falls into the Amazon River. It's pulled apart by piranhas. And that's what happens when something dissolves. Bonding summary done.
So it's interesting to think. I have 2 bonding summaries.
Yeah. Is it?
Yeah.
Probably the same thing, just slightly different. Thank you, gentlemen. Enjoy your day.
Sure.
You have got homework. Yep. No, we still need to spend time on it in class.
Next week.
We'll spend. Yeah. Then we'll move on to all that stuff. All right, cheerio, gentlemen.